Okay, good morning. We're going to go into another section. We're going to finish off Chapter 8 today with Chapter 8, Section 6. And this is just additional topics regarding hypothesis testing. Okay. All right. So the main thing is there is a key connection between confidence intervals and what we are covering here in Chapter 8, which is hypothesis testing. So these two, let's say concepts, these two concepts in inferential statistics are very interconnected with one another. Mainly this: if we are doing a two-tailed hypothesis test and we're simply saying, okay, for the null hypothesis, our population parameter is equal to something, and we give the value. And then for the alternative hypothesis, H subscript 1, we just simply say, okay, the population parameter is not equal to whatever that value was that we had mentioned in H subscript 0. So that would be an instance where we do a two-tailed test. Basically, here's what it is. If we reject the null hypothesis, then that will be exactly when the population parameter is not contained in the confidence interval with the same level of alpha as our hypothesis test. Conversely, if we do not reject the null hypothesis, then that means that our confidence interval with the same degree of confidence or significance will contain the population parameter. So the example that we're going to see here, example 8-30 on page 474. So example 8-30, looking on page 474, here we are talking about sugar packaging. So sugar is packaged in 5-pound bags. An inspector suspects that the bags may not contain 5 pounds. A random sample of 50 bags produces a mean of 4.6 pounds and a standard deviation of 0.7 pounds. So the one thing that I forgot to mention here was chi bar is equal to 4.6. Everything else we have here is mu is equal to 5, so that is the hypothesized population parameter. We have n equals 50, that's our sample size. Notice they gave us the information for the sample. They gave us the sample mean, which I almost forgot. That would have been bad, right? But also they gave us the standard deviation, okay? They said the sample has a mean of blah, 4.6, and a standard deviation of 0.7 pounds. So that standard deviation is that belonging to the sample. It's not the entire population. So here we are, as I had mentioned at the beginning, we're in more of a real world situation where all we have to look at is the sample and and compare that to our what's going on for the population. So for the hypothesis test, we have alpha equals 0.5. And then as a follow-up to this, so after we conduct our hypothesis test, which we might as well go ahead and start doing. After we conduct our hypothesis test, they say as a follow-up, also find the 95% confidence interval for mu. Okay, so here we are doing a two-tailed hypothesis test. We're saying, well, let's see, the thing on the label says it's 5 pounds, and I'm the inspector. This is what I do. I suspect that things may be off. If it were more than 5 pounds, we'd be doing it wrong, right? Giving away too much sugar. If it were less than 5 pounds, also doing it wrong, because we're gonna get sued. So what we're looking for here is just a two-tailed test. Let's use the traditional method. When we're using the traditional method, notice I'm sketching something. You might think I'm sketching the normal curve, but here to remind you that we did not receive the population standard deviation, we're looking at the t distribution. So df is equal to 49. Now, I wrote in df equals 49, and you'll notice that in table, I believe it is table F, yes, table F for the t distribution, you'll see that they skip from 45 degrees of freedom to 50 degrees of freedom, and they don't stop at 49. So we don't have the exact critical t value for exactly 49 degrees of freedom. Now, here's the thing. If we took 49 and we just said, okay, let's round it up to 50, that wouldn't be correct, because we would be assuming that we had a bigger sample than we actually did. So there we would be making an error by essentially overinflating the value of the evidence that we had. So what we're always going to have to do is, if we cannot find the exact degrees of freedom that we need, we will we will go ahead and use the next row up. So whatever the next lower value is for degrees of freedom. So in this case, we're going to go ahead and use 45 degrees of freedom. And so these critical t values that we find are here 2.014. 2.014. And so since this is a two-tailed test, and all of the values that we have in the table for the t distribution are positive, it's up to us to say, okay, well, we have this one over here that's the positive, and then this one over here that's the negative. So there is our critical region. We now have the critical values that form the boundary for our critical region. In step number 3, we're going to go ahead and compute the test statistic. So the test statistic, remember, is a t value, because we're dealing with the t distribution. Remember, we have only the sample information, the sample standard deviation. And so here we are going to do this computation, 4.6 minus 5.0, all divided by 0.7 divided by the square root of 50. So that yields a total of negative 4.04. And so the decision that we make for step 4 is, notice that is where the test statistic is in the picture. For step 4, we would say, reject the null hypothesis. Our test statistic is within the critical region, one section of it. So we reject the null hypothesis, right? And so we say, always in step 5, when we summarize, we say the evidence. Evidence, in this case, suggests And then since we rejected H subscript 0, we're going to go ahead and say whatever we said in H subscript 1. So the weight is not 5 pounds, right? Now, think about this. The significance of a hypothesis test. I mean, you know, not the significance level or the confidence level, but the meaning behind what it is when we're doing a hypothesis test is this. Okay, look, if I grab one random bag of sugar, yeah, it's sugar, right, and it weighs 4.6 pounds, you know, I might just say to myself, oh, okay, well, that's a fluke, right? You know, that the bag tipped over on the conveyor belt, and so, you know, the machine's not doing it wrong. That one was just an odd chance, okay? That'd be one thing. However, notice here, that's not what it is. We've got a whole set of 50 where their average weight is 4.6 pounds. That means, you know, some are going to be a lot under 5 pounds. Some of them might actually be over 5 pounds, but the whole average is actually 4.6. And that's why the t-score or the z-score, whatever our test statistic is, changes fairly significantly to reflect this sample that we took. That's why it's kind of important that we don't overestimate our degrees of freedom. If it's 49, don't use 50. Use whatever you can find that's lower than that. All right, so this is the continuation of example 8-30. This is the follow-up. It said also find the 95% confidence interval of the true mean. Okay, so here we're not, in this case, we're not going to say anything about mu. We're just going to use chi-bar, 4.6, and we know S was 0.7. We want our 95% confidence interval, so that means alpha is 0.05. And for the time being, we're going to pause there and recall the margin of error. This is how we compute the margin of error to form a confidence interval. This is a good review. E for margin of error is the critical t subscript alpha over 2 value times our sample standard deviation S divided by the square root of the sample size n. So the connection between our confidence interval, our 95% confidence interval, and the hypothesis test that we do with a significance level of 0.05 is this. The main thing, the main connection is we have the same alpha, and so we have the same critical t value. Whenever we have a confidence interval or a two-tailed test, the critical values that define the boundary for our critical region and the values for the boundary, the end points of our confidence interval are the exact same under that distribution. Notice here again, we are using the, let's see, we're using 45 instead of 50. Even though our sample size is closer to 50, it is not quite there, so we can't inflate it. We can't make it 50 just because we'd like it to be. We have to underestimate rather than overestimate. So same critical value, 2.014 times 0.7 7 in place of s divided by the square root of 50 for n. And that gives us, well, let's see, it gives us 1.9937, but we're just going to go ahead and round that to 0.2. All right, so our margin of error is 0.2. Our sample size, chi-bar, is 4.6. So the shorthand way that I write it down is mu equals chi-bar plus or minus e. Okay, I just say it's our point estimate. That's chi-bar, and then plus or minus whatever the margin of error is, but that's not proper. Okay, so we're going to say 4.6 in place of chi-bar plus or minus 0.2 for our margin of error. So that we can't leave that like so. So we're just going to say that is the interval from 4.4 all the way to 4.8. And so that's where we're predicting with 95% confidence that mu is located. And so, like I said, I paused for a long time and started to yak it up about the connection between confidence intervals and our hypothesis tests. So what did I say is, I said this: when we reject the null hypothesis, okay, so here's what we're predicting mu to be, and here's our rejection region like this. So we have a two-tailed hypothesis test. So here's our rejection region, right, centered around mu. And here we said, okay, look, our sample average chi-bar fell right here, right? So remember, we're basically saying, okay, when we're doing a hypothesis test, we're gonna look at this interval centered around mu and see what does our sample do in comparison to that. For a confidence interval, we don't have anything to go on for the population. We're just going to say, starting with chi-bar, we're going to build it around this because that's where our distribution is centered. And so our confidence interval is going to extend from here to here. And notice, if our sample value falls inside of the critical region, then that means that the population parameter is not inside the confidence interval. Similarly, if it were the other way around, if we sort of merged these two graphs closer to one another, so that one kind of moves this way and this one moves that way, notice then these two regions would overlap. So if we are not inside the rejection region, that means we're close enough to this population parameter that our confidence interval actually had that population parameter in it, okay? So that's the connection, is that this interval, whether it's from here to here or whether it's from here to here, is the same exact size, right? Okay, so we'll stop there and we'll pick up the next example for the next video.